Okay, so the topic we are jumping into today is the bias-variance trade-off. And before we do, I just want to say real quick that we're all aware that we're in an AI bubble, right? And so there's a lot of energy or emphasis on the internet towards agentic AI, Gen AI generally, right? And I just want to emphasize that companies are still hiring for the core basics, right? So a mastery of these basic, quote unquote, basic concepts is still essential. Hey, all, I'm Drew. I am currently a principal data scientist at a large US bank, but I somewhat recently went through the gauntlet of transitioning from academia to data science. I was a PhD student at the University of Washington in experimental physics. And once I graduated, I realized this career path might not be for me. So that's the context for this channel. If you're anything like me, it is often very challenging to actually come away from watching a video on YouTube with something that you will remember in a week. And I think the reason that retention is so tough is that we're not immediately interacting with the data, interacting with the concept that we're learning about. So with that in mind, in this video, we're going to go through an interactive Google Colab notebook that I've built that you can open yourself and look at a demo in data right now that you can interact with and get intuition on this concept in real time. And again, this is part of our series on an introduction to statistical learning. We're walking through the key concept from every chapter. And this is chapter 2, basically the first real chapter because the first one is just an intro. Okay, let's get into it. All right, so here we are in the notebook. I highly encourage you to open this up yourself. You don't need any special environment. You just need a browser. So if you don't open it now, maybe open it after the video and go through it yourself. So yeah, each notebook is going to have this same outline, the intuition, the math, the demo, and then some quick reminders. So starting with the intuition. What is the bias-variance trade-off, right? It's basically getting at this tension between complexity and simplicity, right? So how do we build a model that learns from data in a way that generalizes well to new unseen examples? So this is the sort of basic plot that you see in textbooks and on the internet. And the basic idea is that with very simple models, you have high bias, low variance, and we call that underfitting. And with very complex models, we have high variance, low bias. We call that overfitting. But we're going to try to get a little deeper into this, like actually see real examples of how you would make a plot like this. So starting with just a very simple example, let's say you have some raw data, right? So you have this plot, you have an x-axis of number of AI roadmaps viewed. So this is your independent variable. And then your dependent variable, or your y, is number of interviews obtained, right? And you want to fit a model to this data. So you start off with a line, right? Linear regression, and you get something that looks like this. So that is high bias, right? Low variance. We'll get into exactly what that means, but this is what it looks like, right? It's underfit. Then let's say you go to a very complex model, high order polynomial that you're fitting to this. You're going to get this wiggle, right? And we can just sort of intuitively see like the data, the line is overreacting to the data, right? And that's just the signature of a high variance fit or model. And then this is that sort of Goldilocks zone, right? Where we have good generalization. Okay, so the summary here is when we fit a model, sometimes it's too simple, right? High bias. It's always wrong in the same way. Sometimes it's too wiggly. It's changing too much with data. It's too reactive to the data. And then also the data itself could just be very noisy, right? That's this spread, and that is the third term in the bias-variance trade-off, which is the irreducible error. Getting into a little more detail with the math here. I don't want to belabor the math because I think the demonstration is going to do a lot more for your intuition than walking through the math slowly. But basically, when we look at the performance of our model, which here I'm going to keep it simple just with MSE. So this is just the squared difference between the predicted and the true values, right? The average over the whole data set. And we look at that MSE, right? Mean squared error. The error comes from three sources, right? The bias squared, the variance, and the irreducible error. So this is just the basic formula, right? That we sort of think of. So in the frequentist view, probabilities describe long-run frequencies if we repeated an experiment infinitely many times, right? So in practice, we can't really do that. We can bootstrap to sort of get at some of these things. So resample with replacement to sort of get a sense of the bias and variance in our models. These are the sort of mathematical definitions, right? We have bias squared is the square of the expected value of our fit, right? That's the model's prediction, minus the true ground truth, right? And this is defined at a specific x value. So intuitively, that is just how far the average prediction is from the truth, right? So if we go up to our plot here, we can see, at x equals 0, we have a high bias, right? Because if I resampled this data from the ground truth, the fit's still going to look just like this, and the distance between these is going to be high. So how far the average prediction is from the truth. The variance at x is how much predictions fluctuate around their average. So this means, like, if I was to resample my data from the ground truth function, right, if I somehow had an random number generator that I could change the seed of in the universe, I would get large fluctuations, right? And so what that means is, like, if I was to resample this data, instead of getting a curve here, I might get a curve way down here, right? It's going to look totally different. Let's now go back up and try to explain two things, which is, why is this a low variance model, right? Why is this high bias and low variance? It's low variance because no matter how I resample this data, right, if I take new data, I'm still going to get basically the exact same fit, right? So the variance is very small. Here, the variance is very high because as I resample, I'm going to get a large change in my fit. But the bias is small because on average, if I was to resample 1,000,000 times, I get the ground truth, right? So the model, any specific model that I train, is sort of overreacting to the data, but on average, over all these sort of potential models I could train, I have good performance. Okay, so that's the intuition for these two terms. And then I have some gory details here, like the actual derivation just for reference. And then I also go into the little bit of detail around, this is the bias and variance at x, right, at a specific x value. But really what we care about is, this sort of overall bias and variance, right? So you have to average over all your x values to get the sort of like generic plots that we're used to seeing for bias variance trade-off. All right, so I ran through the code above, which you should run through yourself. That gets us to the demo here. So this is an interactive demo where you can actually slide these different parameters and understand intuitively how these concepts work together. And I highly recommend just going and messing around with this and asking yourself questions, making sure you really understand what's going on. So what we have on the right here is basically an example fit, right? So We have the true ground truth function, which is that f of x. And then we have some training data in blue and some test data in green. And then red is the fit to the training data. So then over here on the left, we have now, okay, what if I did a fit with each different model complexity, right? So here that's just the degree polynomial of the fit, right? So 0 would just be constant line, right? 0 order polynomial. 1 would be linear regression. 2 would be quadratic, and so on, right? So here I just have an example of a degree 6 fit, and I can change that, and then you'll see now an example of a degree 7 fit, right? Or I could go all the way to a degree 0 fit, and that is just a flat line, right? Okay, so that's the example fit, just to kind of get an idea, basically what these different fits actually look like in practice, right? So then we go to this plot, right? This plot shows both the train MSE, so that's the train mean squared error in blue, which the first observation is, right, this just continues decreasing, right? Why is that? Because as I increase my model complexity, I'm just memorizing the training data, right? So obviously my training error actually keeps decreasing, and it decreases even below the irreducible error, right, which is this green line. And so the sigma on the irreducible error is 0.1, right? So notice that the MSE, the error, is 10 to the minus 2, right? That's 0.1 squared. Okay, so then we have in green the test MSE. This gives us that sort of U shape, right, that we are used to, right? The Goldilocks value is actually, down in here. Fourth or fifth order polynomial would be the ideal fit here, right? Okay, so then we can also mess around with some more parameters. Actually, what else is in the plot that I haven't discussed? So the red line is the example fit. That's the degree polynomial that we see the example of here. And then the green line is the irreducible error. The bias and variance are here too, right? Obviously, we gotta have those. So the orange is the variance, which is increasing with increasing model complexity, and then the bias is decreasing generally. It actually starts going back up, which is an interesting result of this, just the nature of the simulation, right? So I'm only running 100 different experiments to average over, right, to calculate these bias and variances. So if I actually changed this to 600 different experiments, we should expect that this line sort of starts to drop. Now it's like recalculating. So yeah, so you can see this start to flatten, right? So the reason that is because to truly see the bias for these high orders, we need to simulate many, many times the experiments, right? So by experiments, I mean I have some ground truth, right? That is this black line. And then I'm resampling, right? So taking a new set of data and basically averaging over those to get the bias and the variance. But okay, so that's the number of experiments. This is the example degree here. The max degree, that's just the max degree polynomial in the plot. And then we have the train and test number of examples. So this is an interesting one, right? So what happens if I make, this 1,000 for n train, the number of training data points, right? What is going to happen here? Hopefully it runs. Okay, so now we see, boom, that's a lot of training data, right? And what do we learn here? Let's look at these train MSEs and test MSEs. We see, okay, the train MSE just goes down to 0. The test, or sorry, not to 0, but to the irreducible error. The test MSE flattens. It doesn't start going back up, right? And why is that? that is because there's so much data that there's much less risk of overfitting, right? There's so much training data that there's much less risk of overfitting. And this is basically the key concept behind why LLMs can have so many parameters and yet perform really well. They're not overfitting. They're obviously super performant, and that is because they just have unbelievable amounts of data, so they can handle those super high numbers of parameters without overfitting. Okay, and then you can also mess with the number of test examples, and you can also mess with the amount of noise. So let's mess with the amount of noise here. All right, so now what if I turn up the noise? That's going to make this data set way noisier. So what this does is basically mask overfitting, right? So it doesn't look like there's much overfitting happening here, but you don't really want to fit data that's this noisy to this complex of a model, right? Okay, so let's wrap this up with these reminders. So there are 4 reminders here that I've given for the bias variance trade-off. The first one is balance is everything, right? We want to find that Goldilocks zone, not too simple, not too complex, just right. The second is more training data means less overfitting, right? So large data sets keep variance low regardless of model complexity. Not regardless, but even with highly complex models, right? So such as LLMs. And then noise amplifies variance. So in high noise settings, you want to basically default to simpler models, right? And then the last is that the irreducible error is the floor. So you can't beat the noise intrinsic to your data. All right, so that's it for the bias variance trade-off. If you found this style of video, this notebook useful, please let me know in the comments. And I will see you on the next one, linear regression, deep dive into linear regression. Good stuff.